Good evening. Tonight's lesson is over the electromagnetic radiation. Lesson 2 will be reflection in mirrors in my second video. But this is the first lesson in the electromagnetic radiation and optics module. Electromagnetic radiation. These types of waves can travel through a vacuum and don't require a medium to travel through. Produced by a vibrating electric charge and have both an electric and magnetic component. Electric component is actually perpendicular to the magnetic component, and they are in a phase with each other. These type of waves are also known as transverse waves, and we talked about that in the previous model. Here's a picture of the electromagnetic spectrum. The most common use for electromagnetic spectrum is communication. Cell phones actually use these types of waves to communicate with one another, so I'm pretty sure that all of us use this on a daily basis. Check out some of the other types of the range of the electromagnetic spectrum in the picture on the right-hand side. Remember that human eyes can only detect a very small range, which is actually known as the visible spectrum. So you can see that there's radio waves, microwaves, infrared waves, visible, which is the range that we can actually see with our eyes. Ultraviolet are also known as UV rays, which we did a discussion post on tanning beds, X-rays, and gamma rays. The electromagnetic radiation, basically all wavelengths travel the speed of light, and there is a value for the speed of light, which is 3.00 to the 8th meters per second. That is a very, very, very fast. Here is the wavelength equation that you're going to see in some of your practice problems in just a second. And remember that C is the symbol that represents the speed of light in a vacuum. So if you see C, this is the number that you are going to use in that equation. Photons has property of a particle and properties of a wave. The electromagnetic radiation travels through space as a photon. Equation for the energy of the photon can be right here. Can you see it right here? E, remember, is the energy of the photon in joules. F is the frequency of the wavelength in hertz, and H is known as the Planck's constant, which is this number right here. So if you want to add these two numbers to your formula sheet, if you have downloaded the formula sheet, that would be good to know for practice problems. Light, remember, travels in a straight line. It can be deflected in a large gravitational field, but remember, for our class purposes, let's assume that it always travels in a straight line. Light can be reflected, refracted, or diffracted, which we will discuss later, and how this can alter different images. We use something called the ray model, and these are types of models that use the pathway of light represented in a single arrow. This can be used to predict the image location of light. Paths show reflection, refraction, or diffraction of light. So our second lesson in this module is going to talk about how to calculate real versus virtual images using different types of mirrors. So we will be using the ray models to calculate those different images. All right, so we're going to jump into practice problems first. The first one states that a green light has a wavelength of 4.90 times 10 to the negative 7th. I guess this is a typo here. Remember, it's supposed to be 10 to the negative 7th meters. What is the speed of light in a vacuum? So this first question, all it is making sure you know the constant, that the speed of light is 3.00 times 10 to the 8th meters per second. Number 2 is asking you, what is the frequency of the green light? So remember that frequency is C equals F times the wavelength. Remember, that is your wavelength here. So rearrange the formula. So we have the speed of light, which is 3.00 times 10 to the 8th, divided by 4.9 times 10 to the negative 7th. And again, that number is just coming from the problem. Again, that's the wavelength. We put that into our calculator. You get 6.12 times 10 to the 14th hertz. And number 3 states how much energy is 1 photon of green light. So remember, we can use this formula. And we get 6.62, which is that constant that I told you to write down on the previous slide. So the negative 34s times what we just calculated from the part 2 of this problem. So 6.12 times 10 to the 14th. And we should get 4.05 times 10 to the negative 19th. And again, it's asking for energy, so it will be joules. All right, here is the second example practice problem. It says a single photon of gamma ray has 3.56 10 to the negative 13th. It's supposed to be an exponent of joules of energy. All right, the first question is asking what is the frequency of the gamma ray photon. So we're going to be using this equation, which uses that constant again. Rewrite it for that frequency and get the constant divided by the energy. So we get 3.56 times 10 to the negative 13th, divided by that constant, 6.626 times 10 to the negative 34th. And we should get, if you plug it in the calculator correctly, 5.38 times 10 to the 20th hertz. And then question number 2 says, what is the velocity of the gamma ray photon in air? Remember that that would be the speed of light. So again, that's just that constant, 3.00 times 10 to the 8 meters per second. And number 3 is asking for that wavelength of the gamma ray. Sorry. Again, remember that that is that wavelength. I don't know why it always shows up like that. So we're going to plug in what we know, which is the speed of light times to the 8th divided by 5.38. Again, this number was from the part 1 problem that we got up here. And if we plug that into the calculator, we should get 5.58 times 10 to the negative 13 meters. So again, this is some problems that you could possibly see dealing with the electromagnetic radiation. This is going to end our first video for the first lesson of this module. Please stay tuned for video 2.